Hello everyone, let's continue on with our circular motion. As I mentioned before, that circular motion can be connected to the linear motion using some equations. The first equation is what we are going to derive now. For example, you have a rigid object which is being rotated about this fixed axis, and the distance of any point, let's pick a point on that surface, it's from the center is r, and it goes through a change of delta theta, and it goes through the point P, goes through the distance change of delta s, and we know that velocity would be along the tangent. Alright, so basically it's like a rigid object swirled around a point, and we are going to see when the total distance traveled over the total angular displacement, how it is related to the velocity along the tangent. So let's write an equation for starting the same equation that we know of for s equal to r theta. When f changes and theta changes too, so dividing both sides by delta t, this becomes equal to the speed, distance over time, r, this is omega, rate of change of angular displacement. In the previous video, I think I used r here. In that video, it should be s as well, because s represents the distance covered, and distance covered over time would be equal to speed. So this is the derivation of the relationship of the tangential speed or the magnitude of the tangential velocity. That depends on the distance of any point from the center and omega. Since all points go through the same angular displacement change, omega would be the same for all the points. So when it is being rotated, omega is same for all. However, v can be different depending on the distance from the central point. For example, we are very well familiar with a ride called merry-go-round. So on the merry-go-round, we know that it's being rotated, and there are different riders at different distances from the center. So the rider which is sitting closer compared to the rider, which, let's call this point A, point B. So the rider which is sitting at a horse or a lion or something near that axis of rotation, that will have a smaller tangential velocity compared to the one which is sitting here. It will have a greater velocity, and the reason is the point which is further away has to cover more distance in the same time, because they have to stay together. The points are again going to be here and here, so this one has to move at a greater speed so that they both could be in the same line again. Okay, so it is covering more distance, and because of that, the tangential speed would be greater at point B. So VB should be greater than VA. However, omega could be the same for both, since the merry-go-round platform is moving with one angular, the same angular displacement for each point. We can also get the equation for if this is subject to change, if this speed changes, delta V over delta T, r delta omega over delta T. This becomes the linear acceleration. So if V is changing, then there will be a linear acceleration too. There would be acceleration along the tangent. Linear acceleration or tangential acceleration, that would be equal to r alpha. So there are two equations which define the relationship between the linear and the rotational quantities. We can put a little t there because it is this velocity which is directed along the tangent. This is same as the linear speed, and this is the angular velocity, and we can also define at r alpha. These two equations, they would connect the linear quantities to the rotational quantities. Let's work on an example where you have an object tied up to a string, and that string go in a vertical circle. There is again a center. Object could be here, object could be here, and it's going to be at different points at different locations during that circular path. Now when it is here, we can draw. So if it's a string, then there could be tension in the string. At this point, we know that weight will be acting downward. What would be the direction of tension at this point? That would also be downward. And at the same time, the centripetal force is also acting to the center, correct? Because acceleration is directed towards the center. At this point, mg is downward. However, the tension for this time would be upward. So is the centripetal force is also upward. Okay, at any other point, the tension would be directed towards the center along the string, and the weight would be acting downward. So they are not going to be aligned or anti-aligned like this. So you're going to have a minimum value of tension here and maximum value of tension at this point. Let's derive these values. So if at the top, let's work for top first. At the top, we want to know the derivation tension at the top and the bottom. How they vary. At the top, since tension is downward, minus T minus mg, and the acceleration is the negative acceleration as well. This is mv square. mv square over r. This is centripetal acceleration. We can put them together. If I move t on that side, that's going to be mv square over r minus mg. All right. So, at the top location, since mg is already directing downward, it's providing enough centripetal force to keep it at the center. So the minimum value of tension at the top location would be 0. Okay, we know that it's not completely 0 because if there is no tension, the string would go limp. However, it is very close to 0, and velocity becomes equal to RT over m square root. Oh, sorry, tension goes to 0, so this one would be equal to, tension is not there. This would be equal to mv square, mg equal to mv square over r. M gets cancelled, v would be equal to r mg square root. That is the speed it has to have in order to have the zero tension in the string. So it has to go that fast. V should be equal to Rg in order to have the minimum tension in the string. Otherwise, if this value is not up to this value, then it would not, then you would need some tension in the string to keep it on a circle. At the bottom position, we can write the same equation, however, the signs will change. This becomes positive, this becomes positive too, because they both are acting upward. T is upward, mv square is upward, mg is downward. So here we can get the equation for T mv square over r plus mg. So this is the equation for tension in the bottom. Okay. So if you know the speed of the ball in the bottom, and it has to go faster than this position because there is a force acting downward which is trying to pull it down. So it has to go faster in order to keep going. So if we know V and know the mass of the object and the radius, we can find out the value of tension here. For example, the radius of this circle, let's pick some numbers, is about 0.15 meter. So by plugging that in here, we will get 0.15 times 9.8. And then square root it. It gives me 1.2 meter per second. Okay, that would be 1.2 meter per second. If the tension is 0, that must be the speed of the stone at the top. If the speed at the bottom is the problem, now it's just a part of the problem given to you. If V at the bottom is 2 times the V at top, then we get the information about the speed here and we can use it. So let's consider the mass of the stone. Let's make this M equal to 2 kg, and you can plug this here, and the radius of the path, that's another piece of data that we will need, and we already have it. It's 0.15 meters, so we can plug these values in here. 2 times V is twice the top, that means 2 times 1.2 square divided by 0.15 plus mg. M is 2, G is 9.8. If you plug in all the numbers here, you should be able to get the value of the tension in the bottom. Okay, let me get that. This is 1.2. $96.8 plus 96.4 Newton. This much tension it is producing, and it's greater than the weight of the object because it has to keep it going in that circle. So there must be enough tension in order to keep the ball in the center. Let's stop here, and in the next video I will cover the Newton law of gravitation.